name of this talk is kind of as a result of being out in the field in Death Valley with a class. I was asked to do this, and I was wondering, oh my God, what am I going to do? And so I want to show you something which I hope you find new and interesting. If not, you can all get up and just walk out the door, but I hope not. But let me talk about the Northern Embayment Lithosphere experiment, which I think the organizers really wanted me to talk about. I'll give you an update on that, but I'll probably spend most of the time talking about transportable array wave gradiometry. And I also wanted to talk about transfer functions and shallow crustal structure, but I don't have time for that. But is Akram, are you in the, yes, Akram Mustafa Najad, back in the corner there. Besiege her with questions if you want to know how we're dealing with receiver functions in the Mississippi embayment. So here's the story. It's a sob story. EarthScope is very successful, and at the time that this experiment was proposed, there were lots of other experiments, many of them in the western U.S., which also were funded, and they kind of got bumped at the front of the line for the Pascal instruments and the FA instruments. So we started in June 2011 with funding, but with only 6 instruments, which served to basically densify in between TA stations, and we've made about a 270-degree traverse around the New Madrid area with those instruments, and we still have the western side to fill in. And I hear tell that we're going to get 52 instruments starting in June that we can deploy along those profiles that go across the New Madrid seismic zone and down through the axis of the Mississippi embayment. And so actually, I don't have much to show about Nellie as an experiment. However, we have to be busy, and I want to talk about a way maybe of looking at the seismic data just using the TA that you're probably not too familiar with, and this is the idea of wave gradiometry. Here's a map of the TA as it existed something like in March 2012. And I'm going to be looking at a Mali Chile aftershock, magnitude 7.1 aftershock, and look at the waves that come across TA using wave gradiometry. Now, in looking at lithospheric structure, we're always beating our heads against the wall, looking at how smoothly and fantastically these waves travel across the entire array. So you can really see the move out of, say, the P wave here, and this is 125, 150 second surface waves, the Raleigh wave going across the array. That really gives you a very smooth idea of the velocities of these waves. But the signal that we're looking for is in the differences of that wave field. And so TA is great, but how do we actually quantify those differences? How do you get the differences in the wave field to quantify the sort of the granularity of the lithospheric structure? This thing is squashed down. I guess it's okay. And so what I'm going to be doing, this is the only equation I'm going to show, and this is basically Glenn Mattioli told me no more equations at a UNAVCO workshop, so I'll take his, I have to use at least one to show you what I'm doing. But if we have a seismic wave that's sweeping across, just say in the x direction, you can represent that wave as you have a function that's a geometric spreading, and then there's a wave function, which is the slowness is defined by its, or the time dependence is defined by its slowness. Well, there's a compatibility relationship between the displacement gradient, or the wave gradient in space, with the original wave field and the time derivative of the wave field. And these coefficients, this is just using the chain rule on this thing, so everybody who went through freshman calculus can do this. These coefficients tell you, particularly this B1, it gives you the wave slowness, and this A coefficient gives you the change in the geometric spreading, this G primed over G. And so these are parameters that you could get if you have this displacement gradient, the original wave field, and then the time derivative of the wave field. And you can solve for these coefficients. In 2 dimensions, you have x and y. And so you have 2 systems of equations to solve, and you get those coefficients. And basically, you can figure out lots of cool things about the wave. How fast it's going, it's the inverse of its slowness, how the geometric spreading is changing with distance, even how the wave kind of shapes itself in azimuth as it moves along. And so just taking this wave gradient, you can pull out all sorts of different information about the seismic wave. Now, we're going to apply this to TA, and so here's a little circle up here. Here's the TA in March. And what we're going to do is take a 200-kilometer circle and just move it along all over TA and make subarrays out of the TA, compute the wave gradients within that subarray, perform wave gradiometry to figure out the slowness and the direction of the wave, and also something about its geometric spreading change, and then map that. So in a sense, we're going to take point measurements of all these subarrays and then make a tomographic map of these wave attributes. So here's the result for the 125 to 150 second surface waves. We get some really interesting looking patterns here. Now the wavelength of this wave is roughly 400 kilometers. It is basically the move out of that wave train that I showed you at the beginning. The phase velocity, which is 1 over the radial slowness, shows quite a bit of variation. The average velocity is something like 3.8 that you can tell just from looking at the data, yet there are variations, apparent variations in that phase velocity at these long periods that go all the way down to 3 and up over 4. And when you look at it, there are interesting spots where things get slow. There's the Illinois Basin, there's the New Madrid region. There's kind of this granularity to the structure. Not only do you get an instant tomography out of this, there is other information about the wave. Now, if we take a look at the map of the azimuth anomaly, so the wave is traveling along in a certain direction, defined, we usually think, by the great circle path, right? You can look at the anomaly, the difference between that great circle path based on this gradiometry calculation. A negative anomaly means that the wave is traversing a little bit more counterclockwise in direction. Positive anomaly looks clockwise. And so as we see this long period surface wave swept across the U.S., it appeared to be moving in a direction about, maybe 5 to 10 degrees in a clockwise or counterclockwise direction from its great circle path. So there's it's not moving radially in a nice way. And the geometric spreading is even more spectacular. Wavelength of 400 kilometers, there appear to be peaks and troughs in that wave field where the red means that it's dying away with distance. Where you see a blue area, it means the wave amplitude is building up a little bit. Then it dies away, it builds up. And so there's kind of an interference pattern that you see in this data. Now, this really bothers me. This is a very large difference in phase velocity, yet I'm really taking the view that our data are really good. I'm trusting the data. If I trust the data, it really means something when the amplitude says it's doing this or that. But you have to examine this very carefully. Here's the answer or the result for 100 to 125 seconds. If I flip back and forth, you can see that there's some change, but it's kind of basically the same. The geometric spreading kind of breaks down a bit. It becomes more irregular. The phase velocity map, the phase velocity map is kind of the same, but it changes a bit. And so there's some structure to the wave field that's very interesting. So what are we actually measuring? Well, here's the measurement window. Here's a surface wave. And we're measuring, we're getting our gradiometry parameters near the peak of that surface wave, the peak of the group velocity. We're finding the phase velocity, and you can see that the wave attributes that come out of this calculation are very smooth at this period band, and there's very little variation in it. In fact, the average error according to or precision, according to this measurement, is less than 1/10 of a kilometer per second. And we're using amplitudes only. We're not using times, really. So this is just straight from amplitude. And then the wave azimuth down here is also very small variation in it, less than a degree. Now, I don't want to believe that too much. I don't trust it until I beat this problem to death. So here's the error analysis. If you go through and look at all the precision and the measurements, what I just said in phase velocity, I think that the spatial gradient part of the calculation is done well. And so I have great confidence that we're getting the displacement gradients using an array inversion technique. But all these amplitudes or these wave attributes depend on the reference station in the middle of your subarray. The amplitude of that station is very important, and it really depends if that one's doing well or not. If it's not doing well, you take a ratio basically to get some of these attributes, the answer will be off. And so one attempt to get around this is to basically combine beamforming with this array analysis. And instead of relying just on a single seismogram, and here's an example of a subarray within this particular TA group, and the stations that are used to compute the displacement gradients. If we look at the raw data, you can just barely see the red line there is the center station seismogram. This has been bandpass filtered. And we see a little bit of move out of the seismic wave. If we take all of these stations, correlate, and then stack, you get the infinite phase velocity beam. We get this thing, and we take the average of that. That will average over all of the amplitudes of the subarray, and then use that as our reference seismogram to compute these wave attributes. Well, so here's what happens. Not much happens. So I'm getting some confidence that maybe these signals are real. This is the result at 125, 150 seconds Rayleigh wave with no beam forming. Here's the result with beam forming. You can see there's a little bit of change down here in the New Madrid area and in Florida. Basically where there are fewer stations to make an array adjustment. So, but the pattern is pretty much the same in both cases. So I like this. This is it's an interesting way to look at the wave field. The beamforming helps out this wave gradient calculation. It also shows that the TA amplitudes that are observed are very stable. I'm very impressed with the array. It's a fantastic data set to work with. But the next big thing for me is that these wave attributes depend on 3D wave propagation. I'm only going to be able to understand why these things give me the size of the amplitudes, amplitude changes, the azimuth anomalies, by looking at how waves interact with 3D structure. And that's a hard problem, so I can't really do a bunch of 1D problems to figure this out. We have to go to 3D structure. But I think analyzing a data set like this gives you a feeling for what the wave field is really doing, and that's where we really have to concentrate. How can you explain these anomalies, and how do they relate to the 3D structure? And so, to me, that's the next step in seismic analysis and looking at sort of the granularity of lithospheric structure. So that's all I have to say for this one. Thank you.